Uh, so I think we can start. So we have some MCQs based on fatigue, creep, and some hardness related questions. Uh, so first question says that in Vickers hardness test, as you know, there are different types of hardness tests such as Rockwell, Brinell, and Vickers. So you have to say that in obviously in each of these hardness tests we have a different type of an indenter. So it is asking what is the type of indenter that is being used. Is it diamond cone? Is it diamond pyramid? Is it 3 mm steel ball, 10 mm steel ball? In Vickers hardness. So you have to like answer what is the right answer for this. Can anybody try to attempt it?
Diamond pyramid.
Right, we have a diamond pyramid type of wicker harness. It's actually something, if you see something like this, something like this. Uh, so you have a diamond pyramid type of a structure in wicker harness. Okay. So then we have another question that says to get N-type semiconductors, we should add nitrogen, pentavalent elements, trivalent elements, or niobium is added. So you have to form a end, semiconductors. Semiconductors are something such as silicon, germanium type of elements. And in order to make these semiconductors to be used in various applications, we have to make some dopings into it. Either we do a pentavalent doping or we do a trivalent doping, right? In order to form a N-type semiconductor or P-type semiconductor. So you have to say what is the type of element that we can add to form a N-type semiconductor. N means that it will be negatively charged. It will have more number of say electrons in it. So we have more number of electrons and more number of holes. So based on that, we can make a semiconductor, change the properties of semiconductors. So what could be the right answer? Anybody can try to attempt it. For an N-type semiconductor, we are actually making a doping of pentavalent atoms. So option B is right. Pentavalent elements are added to make it an N-type semiconductor. Then we have another question that says that Koppel creep, a creep is a phenomenon where we have some constant loading at high temperatures. So there are different types of mechanisms or different types of equations associated with creep. One of that is Koppel creep, right? So you have to say it is associated to which type of creep. It is dislocation creep, grain boundary sliding, lattice diffusion creep, grain boundary diffusion creep. You have two types of creeps. One is the NH creep, which is we have defined one of the creeps which is an NH creep, we refer to it, and then we have one of the creeps that is called as Koppel creep. So what could be the right answer? Because we have to say at high temperature how will the creep phenomenon behave, and through which mechanism it will be operating.
Ma'am, grain boundary diffusion creep.
Grain boundary diffusion creep, that is yes, grain boundary diffusion creep, this is your Koppel creep. But if you talk about NH creep, then that will be around the lattice diffusion creep, right? It is within the grain of the lattice. For example, if you have a grain like this, you have a diffusion of atoms within this grain, then it would be referred to NH creep. But if it is along the grain boundaries, especially when you have a say small grain size or finer structure, then this Kobe creep is more predominant. So along the boundaries this operates. So you can say grain boundary diffusion creep. Then we have another question that says, on which Rockwell scale is hardness of hardened steels measured? Is it B scale, C scale, both A and B?
C scale.
C scale for a hardened steels, right? So we have two scales mostly in a in a Rockwell scale, and in Rockwell usually have these scales operating for like if you have a very hardened material, then say C scale will operate, but if you have a normal material, then B scales will operate. So this is not a very quantitative analysis for hardness, but it just gives you an idea of the comparative analysis of two type elements, whether they are very hard or whether they are slightly softer. So it is the right answer is C scale. Then we have another question that says, which NDT technique will be suitable for micron size subsurface cracks in a steel component? Is it a visual inspection, magnetic particle test, ultrasonic test, liquid penetration test?
Ma'am, only ultrasonic.
Ultrasonic. Okay. See, for visual inspections, we are having this is something that cannot go for a micron subsurface cracks or below the surface, right? It is more of a surface property. So this is not true. Then we have magnetic particle test. They can also be helpful for measuring subsurface cracks, because if you have a crack like this and you have a magnetic material, then that magnetic material can show some magnetism because of these subsurface cracks. Also, if you put some magnetic particle test, then they can also be like they will have operate with their own north and south poles, and they can also be detected because these are micron sized and they are subsurface cracks. So magnetic particle test can also be utilized. Obviously ultrasonic test is a test which is subsurface, so you have to use ultrasonic test also. And then liquid penetration test will not be true because you have to have some surface open for pouring your liquid or your dye into the material, so that should be a surface crack. So liquid penetration and visual inspection are more for a surface crack analysis, while magnetic and ultrasonic can go to some subsurface crack analysis also.
Ma'am, is it possible to check those cracks which are below surface using magnetic particle test?
It is just a subsurface crack, but if it is inside the material, then it might be very difficult. But if it is on the surface, just some millimeters or some micron level below the surface, so you can do it for using a magnetic particle test.
Ma'am, there is a second query regarding this. Madam, when we should go for ultrasonic and when we should go for radiographic for the cracks which are below the surface, ma'am?
Uh, Radiography is more like ultrasonic is more of a like a quick test for a NDT technique. While for radiography, you have to analyze the surface inside it. I think ultrasonic test is more easier to adopt. So I think
Ma'am, is there a limitation that which type of specimen we have taken, thick, thin, brittle, ductile, magnetic, non-magnetic, when we are
uh,
choosing one of them out of these two methods?
radiographic and ultrasonic.
Yeah, radiographic versus ultrasonic because ma'am, both are used for cracks which are below the surfaces.
Yeah, yes, yes.
So there is a doubt that which method can be used for which type of specimen.
Yes, I'm also not sure about that, but I think it has some properties. It will be obviously dependent on your material thickness. Like if you see, if you have a ultrasound test, you won't have much effect with the thickness. I think so, because if you have a thicker material, then also ultrasounds will pass through the material, and then you can deduct the crack or whatsoever. But
Okay.
I think for radiography there should be some limitation for thickness. I think so, because for radiography also, if you are it is based on your like X-rays you are generated inside the material, and they strike your object, and then you get the image for that crack. So I think I'm not sure. I'm not completely sure about that.
Ma'am, the question was raised by me because there is a similar type of question in assignment 8
Okay.
in which the specimen is made of glass.
Okay.
So obviously we can't use magnetic particle test or
But
liquid
if it is
penetration test,
glass,
I
then
think.
also you have to see if it will. The glass is a transparent material, right? So
Yeah, yeah, ma'am.
X-rays
Yeah.
will X-rays pass through the material, or will they be reflected through the material? You have to consider that also, because for X-rays you have to go for the material. It should pass through the material, and then your crack will be detected. I'm not
No,
sure
ma'am.
about it.
Yeah. So in that case, ultrasonic is a better option, you mean?
I think so. I'm not really sure about that.
Okay, ma'am.
Yes. So we also have another question that says a composite is developed using glass fibers added to polyester matrix. The tensile strength of the glass fiber is 1800 MPa, and polyester is 55, right? So you are given two types of materials. You have a matrix and you have a say fibers in it, and you are given the strength of both. Like you are given the tensile strength, which is 1800 for glass fibers, obviously because it is a ceramic material, so it will have higher strength, while as polyester is having 55 MPa. The ratio of volume fractions of matrix to that of fiber is 1.5. So you are given a volume fraction of like the matrix and your fiber, that is given equal to 1.5. So you have to say what is the tensile strength of the composite, considering that it's a uniaxially loaded material. So you can find it based on your this rule of mixing, right? This is something that you have done. So if you have to find the tensile strength of your composite, that will be equal to the distribution. What is the tensile strength of your material, fiber form, and of the matrix? So your fiber will have something tensile strength of your fiber multiplied by the volume fraction of your fiber, plus the tensile strength of your matrix multiplied by the volume of your matrix. So this will because you have to find the strength of your composite. So this is something that you have to find. You are given the volume fractions of the ratio of the two. So you can try to find the tensile strength of the complete composite. You can try to attempt it.
Madam, option D is the correct answer.
Option
Option B.
B, you mean? Okay, so we will first try to see what is we have to see the value of the we have given the strength of your fiber, that is 1800. So then we have to find the volume fraction of the fiber. We do not, okay, we know the ratio of the matrix and the fiber, but overall the volume fraction will be the summation of the two, right? Volume fraction of your matrix plus volume fraction of your fiber, that will be equal to 1. So you know that the volume fraction of your matrix is equal to 1.5 times the volume fraction of your fiber plus volume fraction of the fiber is equal to 1. So this will be 2.5. Volume fraction of fiber is equal to 1, and then you have volume fraction equal to 1 by 2.5, I think 2.5, right? 1 divided by 2.5, something like this, volume fraction of your fiber. So we can write for this, that is multiplied by 1 by 2.5. Okay, then we have plus your polyester, that is 55, multiplied by the volume fraction of your matrix, that would be nothing but that will be 1 minus 1.1 by 2.5, right? So on solving you're getting this answer. So this is 753 MPa. Okay, so then we have next question that says, as temperature increases, the conductivity of conducting material increases, decreases, does not change. So you are talking about your conducting materials. Normally, this is the most important property for metals that mostly people are researching around. So you have to say the temperature increases, the conductivity of conductors increases or decreases.
Decreases.
Okay. Okay, so yes, the conductivity of the conductive material actually decreases when you are increasing the temperature because of the resistance offered by the metals. So option B is the right answer. Then we
Ma'am, what will be happen if the same question is asked for semiconductors? Is there any definite pattern with temperature if we choose semiconductors?
for semiconductors mostly the conductivity will increase because of the creation of the electron hole pairs. So those
Okay.
will help in increasing the conductivity of a material.
Okay. Thank you.
Yes. So actually in conductors mostly there are like resistance offered with increase in the temperature, because as the temperature increases the molecular or atoms, they move, they vibrate at their positions, and because of those vibrations the movement for your conductive electrons is hindered. So overall the conductivity is decreased. Then we have another question that says, extrinsic semiconductors are doped with pentavalent atoms, doped with trivalent atoms, both A and B, pure semiconductors.
Ma'am, both A and B.
Right, both A and B, because we have two types of semiconductors where we say we have intrinsic semiconductors. They are actually pure elements, such as, for example, silicon. But when you are doping it with some agents such as pentavalent or trivalent atoms, they will become extrinsic semiconductors. And this is a very important aspect of semiconductors currently. If you see your solar panels have these silicons in them, polycrystalline silicons, right? Generation 1 semiconductors, generation 1 of solar panels, they have these silicons in them. So they have solar cells, so they are very high purity silicons using, and they have some dopants also added to it, so for its electrical conductivity and so forth. Also the silicon is an important aspect in your chips. If you know, you have some semiconductor chips known as integrated circuits, they also contain these silicons. So these semiconductors have an important role to play in your electronics and in your like renewable energy sources. So mostly they are doped with certain elements, and also if you know, if you have sources like LEDs, your LEDs contain, which are your light sources which you are using. those LEDs contain gallium nitride in them. So that is also one of the nitride is a dopant here, and then they also have gallium arsenide type of structures, right? So these are different types of structures that are being used for uh, electronic industries. So semiconductors are crucial for for electronic industries. Then we have another question that says hard magnetic materials are suitable for permanent magnets, transformers, solenoids, or none of the above. So you know hard magnets, there are two types of magnets, one are hard and one are soft. Hard magnets are something which retain their magnetism and it is very difficult to remove their remnant magnetism. They always have some remnant magnetism. Well, soft magnets are having a very small reminiscence or cohesivity in their magnets. You understand it by using a hysteresis loop like this, in which if you have a very broad type of curve, then it is called as to be a hard magnet. But if it is having a very small loop, then it is a soft magnet. But you have to say where this hard magnet and soft magnet will be applicable. So, will hard magnet be used in permanent magnets, transformers, solenoids, or none of the above?
Permanent magnets.
Right. So, permanent magnets are the utilized for hard magnets. There are various types of like this is a common example for us like transformers or solenoids. We understand they have some eddy currents going into them, and then they transform the energy. They increase the voltage. However, for permanent magnets, we mostly have examples of our ferrite magnets. We have they are called as ferrites, and we also have very important class of magnets known as rare earth magnets. They contain rare earth elements in them. They are an important and crucial component of like renewable energy source. Like your wind turbines have rare earth magnets. Your also hard disk drives have rare earth magnets. So these permanent magnets are hard magnets, and they are of these types like ferrites, rare earth magnets. They have some formulations like these Nd2 Fe14b. This is a type of an alloy that is being formed for these magnets. So this is an alloy that is formed and it behaves as a very hard magnet and is used in various applications. So rare earth is because this Nd is a rare earth element. So this is utilized in these applications. Then we have another question that says,
Ma'am, excuse me, ma'am.
yes,
Ma'am, like these FM radio sets or any radio set we are using for listening music and news.
yes.
Ma'am, which type of magnet is used in
They will
radio
also
sets,
have
ma'am?
some rare earth type of magnets in them. They might have some other like the composition changes like this Nd2Fe14b remains mostly in your hard disk drives or in your wind turbines. Sometimes they are also using some like dy, which is dysprosium, or they are using some dopants of say this gadolinium. So depending on what kind of application it is, like your mobile phones also have speakers. The speakers in your mobile phones also have rare earth magnets. They have some gadolinium in them. While as if you have
So,
some,
ma'am,
yes, yes,
so do you mean we are using hard magnets in them?
yes, yes, they are permanent magnets that have been used.
Thank you.
So, and also like these have permanent magnets, they retain their magnetism, but only if you heat them above a certain temperature, like Curie temperature, they lose their magnetism. So you have to operate the machine below the Curie temperature so they do not lose their magnetism. So, okay, next question is that we have a silicon carbide coated boron fiber for the reinforcement in the aluminum matrix. In our previous case, we had a like the reinforcement question we did there. We had a glass fiber and we had a polyester. So we had a matrix of polymer and we had ceramic material as a reinforcement. Here we are having a ceramic material silicon carbide as a reinforcement, and then we are using a aluminum matrix, which is a metallic matrix, right? So it can be a metal, non the like the reinforcement in the matrix types can differ. Like they can be ceramic and polymer. They can be ceramic and metal. So there are different types of combinations that can exist. So we have determined the elastic modulus of a composite containing 40 volume percentage of fiber. So we know the volume fraction of our fiber, that is, we can write it as 0.4, right, in fraction. And it is written that it is parallel to the fiber axis. So you are having a composite material like this, and you are pulling the material in the longitudinal direction. So the fibers are arranged in the longitudinal direction only. This rule of mixing is only applicable when you have the fibers aligned along the vertical, along your like principal axis or along your fiber axis. Otherwise, if you can also have a combination where these fibers are in the transverse direction, so there this will not be applicable. The same formula will not be applicable. uh, then that will be a different case. So, but here we have operating tensile, like the force is acting along the fiber axis. So we can apply the rule of mixing here. So you are given that the modulus of your aluminium is given, the modulus of your fiber is given. So you have to find the modulus of your composite. So the modulus of your composite will be equal to the modulus of your, say for example, matrix, and the volume fraction of your matrix, plus the modulus of your fiber and the volume fraction of your fiber, right? So you understand that your modulus of your matrix, the matrix here is aluminium, so it is 69, and the volume fraction of your matrix will be 0.6, because we know the total fraction will be 1. And then we have another, that is modulus of your fiber, that is 390, 379. Then we have a volume fraction of your this, that is 0.4. So you have to say what will be the modulus of your composite. You can try to calculate it.
193.
Okay, 193 is the right answer. I think yes, 193 is your value for the composite, right? So it is always in between the modulus of your matrix and the fiber. So the modulus of your composite will be in between of that. Okay. Then we have another question that says that below which point does fatigue occur? So you know what fatigue is? Fatigue is the cyclic loading that you are applying on your material. So you have to say at what point the material will fatigue, because fatigue is nothing but it is a fracture. It is a form of a fracture that occurs because of your cyclic loading. So you have to say below which point does a fatigue occur? Ultimate strength, fracture point, elastic limit, or yield point.
Yield point.
Right, yield point. Because we always say that fatigue is a catastrophic failure that can occur when you have a cyclic load applied on your material, and the material will have a tendency to fracture even below its yield point. So option D is right. Then we have another question that says the SN curve for mild steel never becomes horizontal line. True or false? So you know you have an SN curve for your, this is your S curve, this is your N curve. You understand that after applying n number of cycles, the stress that the material can endure, or the stress that can be applied on the material, changes. So you have something like this curve, these curves. This is for say for example steel, or you have something for an aluminium. This is something you have covered in the class also. So you see that for steel, the question asks that it will become never horizontal for a mild steel. Is it true or false? This is actually
False. False.
false, right? Because it becomes horizontal after certain number of n cycles of fatigue. That means you can put the sample through n number of cycles through that specific number of fatigue cycles, and the material will not fracture. So this is your, for example, for steel, and this is for your, say for example, aluminium, right? So this is your SN curve, typical SN curve. Then we have another question that says that the fatigue life of a part can be improved by, what is the mechanism by which we can improve the fatigue life of a part? For example, you are given a part, how we can improve the fatigue life? You know any method by which we can improve the fatigue life?
Ma'am, by introducing the compressive forces on the surface.
Right. So we call the method as short peening, right? So by this method, we are imposing compressive forces on the on the surface of the, say for example, fatigue, sample undergoing fatigue. So that will result in, for example, next time, because you know the material is undergoing tensile and compressive stresses. So it is actually only during tensile stresses that the material undergoes crack initiation and propagation. So if the material is subjecting to a tensile stresses, the chances of it getting cracks to get propagated will be more. So you are just inducing compressive stresses on the surfaces so that your cracks, so that next time when the tensile cycle comes, that will, a part of it will be utilized in overcoming the compressive stresses, and only a part of it will be utilized for crack propagation. So it will try to delay the fatigue that can be occurring in your material, so you can improve the fatigue life. Okay, so then we have another question that says that the creep rate in ternary stage. You understand that, you have understood for a creep, you have drawn some characteristic, because creep is nothing but it is a deformation at a high temperature, right? So you have drawn for a creep, a typical curve for a creep is shown like this. This is your x and y axis, and then you have some like this variations, right? You have three stages of creep. You have first stage, second stage, and third stage. And you have to say that the creep rate in the ternary stage, that is this stage, is decreases, constant, increases, or none. Obviously, as we have seen, this is your creep rate. So this creep rate is actually increasing in your ternary stage because it has overcome all the hardening in the material. Now, at higher temperatures only, what happens? The strains will be accumulating in the material and it will result in the fracture. So, the right option is C. For a creep rate in a ternary stage always increases. Then we have next question that says that the ternary stage creep is associated with dash, strain hardening, recovery, necking, or none of the above. So, what is the right answer for this?
No, I think necking.
Yes, for the ternary stage, actually in the first stage we are actually undergoing strain hardening. Then in the second stage there is a complementary of the recovery of your strain hardened material occurs, because you know if you are increasing the temperature above recrystallization temperature, there occurs the removal of some stresses inside the material, and then the grains are stress free. They are called as recovery, and then after that, if you're increasing it further above certain temperatures under a constant load, then you will result in the necking, or it will result in fracture of the material. So option C is right. Then we are then we, then we have another.
Ma'am, I have a question regarding creep. Like in some books, it is said that creep can occur even at normal temperature if we stress the material for longer period.
Yes.
So, ma'am, my question is that is high temperature is necessary to creep to happen?
For creep necessary to happen, you should have very low strain rates. Mostly, the concept is of strain rates, but we tend to expect it in the form of temperature also. But you have whenever even if you have low strain rates, you have a material under a constant loading, then creep can occur. It depends on the material.
Because, madam, many times it is asked that whether creep is a function of time, temperature, or both, ma'am.
Yes.
So, is it function of both or is it a function of time only?
Like
That was my
when you
actual.
undergo any creep test, you do it at a certain temperature, but you keep the temperature constant, and then you change your you go for elongated times. So it in that case it is a function of time because you are placing it at a working condition, certain temperature, and then you are keeping it for say 3 hours, 30 days, 60 days, 90 days, something like that. So it will be a function of time then, right? So we have this question also there where we have a total strain rate in a creep test is what? It is less than 1%, around 10%, around 50%, or greater than 50%. So you have to say it is a creep. How what are the strain rates that are applicable in your creep? So in this question, we have a strain range for given for a creep. It is actually only small strains are given in a material. That is why we say that less than 1% strains are given for a creep sample, and then we can say that the material is undergoing creep testing or creep phenomenon. So we should have very small strains acting on the material. Then we have another question that says the Vickers indenter has dash angle between the opposite faces of a diamond. So what is the angle? Is it 90 degree, 120 degree, 136 degree, or 180 degree?
136.
Yes, 136 is the right answer. Then we have another question which says that why Brinell and Vickers hardness test results show similarity. Like you know, Brinell hardness is like you have three types of hardness ways. One is Brinell, one is Rockwell, one is Vickers. Most often, whenever you do Brinell testing, you will have a similar results in your Vickers hardness also. So is it because of a material indenter or it is geometrically similar indentations? Applied load is same or same size indenter? You should know for this that what are the indenters being used in your Brinell. In Brinell, you have two types of indenters used, while as in Vickers, you, as we discussed, it was a pyramid that was being used. Earlier, we said that it has a pyramid type of indenter being used, which is at an angle of 136 degrees Celsius. 136 degrees, sorry. So you have to say why Brinell. Brinell has around two types of indenters. So one of the indenter is steel based. One of the indenter is having like we have two types of for example if you see this Brinell and Rockwell, sorry. So for Rockwell we have two type of indenters which are based on your say for example what kind of a scale you are operating. So but for Brinell, so I'll write here Rockwell. So for Rockwell, we have two types of indenters, and they are based on what type of scale you are being operating. So you have a Braille indenter, which is the like cone type of a indenter, and you also have one type of indenter which is based on steel balls. And then you have Brinell. Brinell is having a characteristic form of your steel balls, and around, I think they are 10 mm, if I'm not wrong. I think they are 10 mm sized steel balls, which are used for your indentation. So if you say they are having the same material indenter, which is wrong, because here you have a diamond pyramid used and here you have a steel balls being used. So the similarity cannot be based on your material indenter. Then it is saying that your applied load is same. Also, the load will not be same in Brinell and Vickers. So this is also not true. Now we have two options, whether it is geometrically similar indentations or it is same size indenter. The right answer is it is actually the geometrically similar indentations that are being formed. When you are putting a Brinell indenter on a material, you are measuring the depth of the impression, and also during Vickers, when you have a Vickers test, you have geometrically similar indentations that are being produced in the material. And you are just measuring their diagonals, or you are measuring the length of your indentation for calculation, either for a Brinell or for a Wicker hardness. So I think the right answer will be the geometrically similar indentations. That will help in you getting a similar results for your hardness test. Then we have these questions. We have first question where you have to match the properties and their like testing methods. For example, ductility is a property of a material that you need to test. Then is endurance limit, then is toughness, then is resistance to penetration. So you have to match them with the type of a test that you have to do for measuring these properties. So for example, for first, if we see ductility, right? So ductility will be matching to what? So ductility you can use
Tension.
using through tension. So we can write A here. Then we have endurance limit. Endurance is something that is related to fatigue. So we can say B. Then we have toughness. Toughness is measured by impact test. If we have, I think we have not covered, but there are different Charpy test type tests that are used for measuring the toughness of a material. So this is your impact, and your resistance to penetration is your hardness. Always the resistance to your penetration or resistance to your stick deformation. So that is hardness. So the right option will be, I think, C. Option C will be the right option. So next question you can try to answer. It is important to know what kind of measurements we are doing in what type of a hardness, right? This is your question, which where you have to match your hardness types with the type of results that we are actually measuring. For example, for a Rockwell hardness, what kind of a measurement is taken of the indentation for determining the hardness of the material, right? So similarly for Noob hardness, Vickers hardness, and Mears hardness. So this is a common question that is being asked. So for example, Rockwell hardness. So for Rockwell hardness, what do we measure? Do we measure the unrecovered projected area, surface area of the indentation, depth of indentation, or projected area of the indentation? For Rockwell, yes, we measure the depth of our indentation. So this is right. Say for example, you are aware for the Vickers at least. For Vickers hardness, what do you measure? You always take the Vickers hardness test for a material, and then you take it under a scanning electron microscopy, and then you measure the diagonals of the, say for example, your Vickers hardness, right? So you are actually measuring the surface area of the indentation in your Vickers hardness. Okay, so we write here R. Then we have Noob's hardness and Mears hardness. I'm not sure if it has been covered in the class, but for example, Noob's hardness, it is always the unrecovered projected area that is being measured. Because whenever you have a, for example, you have a indenter, you are putting it on a material. Once it has gone inside the material, it has deformed to some extent. And once you remove the load or you remove your hardness tip, there is some unrecovered projected area of the indentation that is being measured on the Knoop's hardness. There is some recovery happening inside the material, and there is some unrecovered area. So the Knoop's hardness is always measured for the unrecovered area of the indentation. So this is Q. And for say for example Muir's hardness, then we have a projected area that is being measured. At least for Rockwell and Wicker, you can keep in mind that in Rockwell you are measuring the depth of the indentation, and in Wicker you are actually measuring the surface area of the indentation. So this is at least which you can remember. Rest two you can skip because I think they have not been covered. Then we have the question for your entity technique. Okay, so this is something which of the following is a function of a developer. This is mostly used in your liquid penetration testing or some dye penetration testing. So you are provided options with providing a contrast background for visible dye indication, making the penetrant water washable, penetrating into discontinuities open to the surface, or dissolves organic soils.
Option
Option
first
first
option.
option, ma'am.
Uh, for a developer, you are providing a contrasting background for visible dye, or you are making the penetrations water washable. Okay, you are actually which of the following? So you have this. At least this is not the right option. The dissolving of the organic soils and making the penetrant water washable, right? But don't you with the help of a developer, you are allowing the penetration to go into the surfaces. So which of the which of the component of your liquid penetration is used for putting the material into the discontinuities?
Ma'am,
Ma'am,
I
I
think
think
option
option
A
A
is
is
the
the
only
only
answer.
answer.
Okay, so if you have seen a develop, I think the option C could be the right answer because when you are putting a say for example a developer on a material, it has to actually the purpose of the penetrator is that it should pull out your penetrant out of the defect so that it can be seen, right? So not only it should provide the contrast, but it should also be able to pull back your penetrant from the defect. So basically, when you are putting you are putting a dye inside a material, and then you are putting a developer on it. The developer should have a properties that it should pull out your dye material out of your say defect or crack, and then it should be make the surface visible. So by change of your color, you can see by visually. So it is actually it should penetrate into the discontinuities, and then that will pull out your sample or dye for your better visibility. I think option A is also right, but the function is not only for providing a contrast but also to pull it from the crack or defects and make it visible. So then we have another question which says that a Prel indenter used in Rockwell harness has the following geometry and material. So yes, we said that we have two types of indenters in the Rockwell. One is Braille indenter and one is a steel ball indenter. So the geometry of your Braille indenter is square base diamond pyramid 136 including angle. This is not true because this was for Wicker hardness. We saw that. Then we have conical shaped steel with 120-degree apex angle, conical shaped diamond with 120-degree apex angle, 10 mm diameter hardened steel balls. Obviously, this is also not true because this is a Braille indenter, not a this steel ball indenter either for a Brinell or a scale B type of an indenter. So now you have two options. Which of the two is right? Is it a conical shaped steel with 120 apex angle, or it is conical shaped diamond with 120 apex angle?
Ma'am, what is mean by braille word here?
Braille indenter is it is the name for the indenter that is being used. There are two types of indenters being used in Rockford.
So, does it belong to only one scale, you mean?
Yes, it belongs to one scale only. Yes. Braille indenter is only used for scale C, like for hardened materials. Yes, for hardened materials, it is used for scale C.
Option C is the correct answer.
Right. So conical shaped diamond is the right option. It's not a steel that is being used, but the diamond with 120 apex angle. So this is the right option. So I think that is all for today. If you have any question, so I think that is all for today.
Ma'am, I have two queries in the week 7 assignment.
Okay.
So, can I share my screen with you, ma'am?
Yes.
Ma'am, is it my screen visible to you?
Yes.